Good evening, Internet. I am Matt Booyak, and in this video we'll be taking a look at the 49th problem from the Project Euler Problem Archive. Now, this problem asks us to find three 4-digit numbers such that they have the same digits the same number of times. That is, they are permutations of each other, with each number being prime, and the three numbers forming an arithmetic sequence. That is, the difference between the first two is the same as the difference between the second and third. The problem says that there are two such sequences and gives one as an example. And we are to find the other such sequence. Now, the approach that we're going to take for this problem is to find all the ways of selecting 4 digits out of the 10 possible, taking into account that repeats are allowed. But we want to do so in a way that doesn't consider the same selection multiple times. Once we've identified all the possible ways of doing this, for each one, we will generate all the possible permutations of that selection of digits. And the way we'll do that is using this function here, next permutation, which does exactly what it sounds like. We'll start with the items in non-descending order or sorted order, and we'll use next permutation to consider each of the possible permutations, and this function will return false once we've considered every possibility. You'll note that for 4 digits, if the digits are distinct, there will be 24 permutations. Lastly, we'll consider all the ways that we can select 3 of these permutations and test that they are that they do in fact form a sequence. You'll note that if we start with the digits in non-descending order and use next permutation to generate all the permutations, the numbers will already be in increasing order, and so that will make it very easy to check if they are a sequence. Okay. The one final thing that we need to consider before we start writing some code is how are we going to generate all of our selections in a way where we don't repeat the same selection. And the way we're going to do that is just to take each 4-digit number, or each number with 4 or fewer digits, and check to see if the digits are in non-descending order. You'll notice that there's only one way of arranging 4 digits, be they distinct or not, in non-descending order. And so if the digits are in that order, that will be the unique instance of those digits that we will consider. I don't know if that exactly made sense, but perhaps it will become more clear once we get into writing some code. So let's do that now. As usual, we'll copy our template directory to make our problem directory, enter our problem directory, and open our main.cpp. Okay, so as I said, we want to consider all of the numbers less than 10,000. So we'll say int n for n is equal to 1, n less than 10,000, increment n. Okay, so now we want to check for our given value of n that the digits are in non-descending order. And fortunately, there's a very simple function that will help us do that. This isSorted function here. But it does require that we break out the individual digits. It doesn't work on, it works on containers, not on integers. And so we'll convert our number to a string and see that the characters are in non-descending order. Note that the character code for a given digit will be greater than another if and only if the digits are greater. That is, the character code for 9, for example, is greater than the character code for 2. Okay, so let's use that. We'll go back here and say is non-descending in n. And we're going to convert this to a string first, so we'll need to say include string. Say std string digits equals std to string n. And then we'll just say return is sorted digits.begin digits.end. And in order to use is sorted, we will need algorithm. We'll also need to include this for, to use next permutation. Okay. So down here we'll say if is non, or if not is non-descending, n, continue. That is, the arrangement of the digits in n will be, there's an arrangement of those digits that is in a lexicographically earlier arrangement. And so we will discard this arrangement of the digits and only consider these digits with a different arrangement to avoid duplicating our work. Okay, so let's just break out the rest of the logic into a separate function here. So we'll just say try1. This is going to do the rest of the logic for a given value of n, or a given selection of digits. Okay, so we'll say try1 is going to take an integer n. One thing I just realized, in addition to the other logic that I described, we're going to need to check if these numbers are prime. Going back here, yeah, where it's required that each of these numbers are prime. And so we'll be using the primes class that I wrote a while back in order to do that. So let's say include primes. And we'll also need to change our make file to include the library where that is implemented. That's our number theory library. Okay. So now we need to generate all the possible permutations on n. So we're going to store those permutations in a vector. And so let's include vector. Say std vector int perms. Note that in order to generate the permutations, we're going to convert our number here to a string so that we can easily permute the digits. But once we've generated the permutation, we're going to convert it back into an integer. And so let's say std string digits equals std to string n. Okay. Now, before we start rearranging the digits, we don't want to forget the fact that the current arrangement of digits is also a valid permutation. So we want to consider that first before we start rearranging things. And so we actually want a do while loop. We're going to say do while std next permutation digits dot begin digits dot end. Okay, so for a given permutation, we want to convert it back to an integer. So we'll say int perm is going to be equal to s to I of digits. So this function here, s to I, just it does exactly what we want. It converts from a string back to an integer. Okay, so first we need to make sure that this integer actually has 4 digits. So we'll say if perm is less than 1,000, continue. That is not a valid permutation for our purposes. Then we'll say if not p dot is prime perm continue. You know, it's funny because in my mind, when I added this include primes.h, I also added this here, but in reality, I did not do any such thing. Let's add that there, and also declare that down here. Okay, so we've checked if our permutation is has 4 digits and that it's prime. And so this should be a valid permutation. So we'll say perms.pushback perm. Now, lastly, we need to select 3 of the permutations and check to see if they form a sequence. In particular, we have to consider all ways of selecting 3 of the permutations. And so we're going to say well, first we're going to say int size equals perms.size. And that's just because this perms.size returns an unsigned value, and we want to have a signed value. And I'd rather just do this conversion in only one place. Okay. Now we'll say I is equal to 0 going up to size minus 2, increment I. J is equal to I plus 1, size. I'm getting ahead of myself. Size minus 1. And then for int k is equal to j plus 1. K is less than size. K is less than size, increment k. Okay, so what is this horrible mess of for loops? It's really not as bad as it looks. Basically, I just want 3 indices chosen from, ranging from 0 to size minus 1, such that I is less than j is less than k. And I believe this, if I haven't made any more typos, this should achieve that. Okay, so now let's get our 3 permutations that we're going to check to see if they form a sequence. So we'll say int x equals perms I, int y equals perms j, int z equals perms k. And then we'll say if x or y minus x is equal to z minus y, %d, %d, %d. X, Y, and Z. You recall I mentioned in the intro that because we're generating our perms in lexicographically ascending order, that means that the resulting numbers will be in increasing order, and so we don't have to worry about sorting these. We can just take the difference just like this to see if they form a sequence. One other thing you'll note, I'm not terminating at this point. I actually wanted to print out both solutions just as a sanity check. We can see that it finds the other solution that was mentioned in the problem description here. Okay, so let's see if this works. Go back over here, make. That's unusual that primes.h doesn't seem to exist. You know what? I bet there's a mistake I occasionally make. Yes, this num theory can go almost anywhere, but you can't put it between the dash capital I and the location of the library. It has to go over here. There we are. I've made that mistake before. Okay, let's run solver, and we see that we have our the solution that was mentioned in the problem as well as one other, and our answer is just going to be these three numbers concatenated. So that's 2969, 6299, 9629. All 2s, 9s, and 6s. Very interesting. Okay, so let's go back to the archive. I almost certainly have been signed out. And sign in here. Okay, and we'll scroll down to prime permutations. And we'll see that this monstrosity, I don't know why the calculator's here all of a sudden, this monstrosity does in fact match our answer. So as always, thank you for joining me. In the next video, we'll be tackling problem number 50, the big 5-0. It's not that big, but we'll be tackling problem number 50. See you there.